Okay. So we're still following the first lecture on my course from Utah. Shivi is responsible for the camera. מקליט, לא?
מה אתה מקליט?
שיראו את שיבי. כן, עומר, אתה שם את זה ביוטיוב.
אני לפני שנה כבר ראיתי את ההרצאות של עומר ביוטיוב, שעומר הקליט ליוטיוב.
So I'm still following the first lecture from this lecture note, which was 1 hour. At that time I was faster than today. I noticed that the second video was very bad quality, so I will try to write large and only with black and blue, and only if there is something that I don't want Yakim to see, then I can write it. Yeah, okay, so we continue with some basic properties of lattices. And I recall the classical theorem, which is called Poincaré. Going to help me here. This, the currents are with me here. It's a very okay. Poincaré recurrence theorem, it's a very elementary statement, but extremely useful. So with the following, so let x and be xm t be a probability measure preserving system. So it means that t acts on x, preserving the measure mu. And use the probability measure, let omega in x be a measurable positive measure, then Tn omega intersect omega non-trivially infinity omega. So I don't know how is the video. So Yakim, can you read this?
Not when I see you.
צריך להזיז את הלוח טיפה, את המצלמה.
תסדר את זה איפשהו שהם יוכלו לראות. And tell us if you can't read or can read it because
When you focus on the board, yes, we can.
This is good.
But when we see you, no, we can't. We cannot.
זהו, אז זה אפשר לראות?
Yeah.
Okay, good. So, and the proof is even shorter than the statement. So, just say proof. So the proof is just look at the set Tn omega m of this is constant. Implies there are n which is not m such that t to the n omega must intersect t to the n to the m omega, which implies that t to the n minus m omega must intersect omega. Okay, and you can take it such that the difference between n and m are as large as you want. For instance, you can only look at only large enough jumps. You don't consider all integers. Yeah, I mean, from this, you add another line of details, and then you see that. So that's an easy statement, but extremely useful. And one application is when you apply it to lattices. So use a lemma that follow. So let gamma in G be the lattice. Now this is a completely general statement. So G is a locally compact group and gamma is any lattice. Let I don't know, gamma in gamma and omega in G ID neighborhood. Then there is n arbitrarily large such that gamma to the n so not what I want. Let G in G and gamma. Then there's n arbitrarily large such that G to the n is omega close to gamma. Omega, let's say, symmetric ID neighborhood, omega G to the n, omega intersect gamma non-trivial. So this has many. Okay, this is immediate application of the previous result, right? You just look at the action, so the proof. Consider G acting on G mod gamma with a normalized measure. And for G in G, just apply the following. Consider G to the n acting on G mod gamma, and this is immediately if you copy the statement of Poincaré recurrence to this situation, then you can get that. And the application is there are plenty of applications. So for instance, how do you apply it? So example, so let G be SLN R and gamma lattice. Then consider G to be the following matrix 2.
It doesn't not only intersect gamma, it intersects the identity.
Sorry?
Specifically, can't you take instead of gamma even the identity element? Can't you take instead of gamma even just the trivial subgroup here?
No.
Well, I mean, so
Like
if you multiply for
this will be like typically this set will be very large. So what you do typically, the picture you should imagine, this is G, this is the identity, and this is some identity neighborhood, and you take some G inside G, which is very large. So then you start, this set start to wander in G and go farther and farther. But somehow, yeah, okay, it's not a typical example, and then it must intersect gamma infinity, very far from. But the set also is not the metric that does not preserve. It will be distorted because there's no bi-invariant metric on G, and you multiply from left and from right, so it's distorted. But still, You can use it, for instance, if you take G to be some elements like that, A1, A2, up to AN, such that AI is much bigger than AI plus 1, like powers of 2, for instance. Then you apply it to that element, applying the same, to powers of G, and small omega, one deduces that that gamma contains a semi-simple element. Similar, so you can start to play with that, and you can get many. So okay, this will be an exercise. And in fact, this Poincaré recurrence, which is extremely elementary, you can also deduce the Borel density theorem from that. So let me give another exercise. I will give another proof of Borel density theorem later. We'll give the Fürstenberg proof, which has the advantage that you can generalize it to invariant random subgroup. Maybe also this, I never thought about it, maybe. But here is an exercise. And this is like, if you want, Borel density theorem. But it's not the full version of Borel density theorem. So let gamma inside SLN R be a lattice, then the span of gamma of the matrices is the full matrix algebra. So which means in some sense lattices are big, algebraically big. This is of course, if you know Borel density, then this is a follow from Borel density, but it's almost the right statement. And you know, many of this, what I'm doing now, is contained in the paper by Selberg from 1962. It's a wonderful paper that maybe didn't get enough recognition. So it was before, just the beginning of this theory of lattices that was evolving. And Selberg actually, his motivation was to prove local rigidity, which I'll say later what it means. It's the beginning of rigidity theory in a sense. And he didn't, the term lattices was not exist at that time even, so it just considered a co-compact discrete subgroup of SLNR, and it proved such statement and the dispersion of Borel density and many other stuff. What people remember today from this paper is what's called Selberg's lemma, that finely generated linear group is virtually torsion-free, which I think actually was proved earlier by Wilcoxon. So maybe Selberg proved a more general statement, but anyhow, this paper is full of very elementary and very clever ideas, and which later influenced Mostov and Margulis to develop the rigidity. But this, for instance, you can find the proof of that in this paper, but and as well as other things that I will do today. But you can do it yourself. You just play with matrices. You take such matrix, such unipotent matrix. I don't know. For instance, and start and take powers of it, then you will see here something like that, and then you know that near such a matrix you can find an element in lattice, and you use such things to. And yeah, okay, I'll let you do it. And yeah, okay, so this is one thing.
Tsachik,
Yeah.
what is the definition of semi-simple element?
A semi-simple element is an element such that semi-simple, or I want not just semi-simple but even regular. Semi-simple in SLN, semi-simple means that it's diagonalizable. More generally, it means that adjoint, I mean, if the group is not given as a matrix group, the adjoint, so if you act by conjugation on the Lie algebra, then you get a linear representation. So the adjoint of the element is diagonalizable over the complex number. It's equivalent for semi-simple group to say that the conjugacy class of the element is closed. That semi-simple element. Regular means that the eigenvalues are do not coincide as much as possible. So in SLN you can take them all different. In other group you are forced to. You cannot take all of them different in general, but you want to minimize the repetition. So basically, regular means that the centralizer has minimal dimension. So here in SLN, regular semi-simple means such an element or something that conjugate to such an element, such that all the AIs are different. Now, if you take large gap between them and start to raise power, so the gaps even increase, and then you can deduce from this Poincare recurrence that near such an element, you can find an element in the lattice, and an element which is close to semi-simple is also semi-simple. I mean, that's the idea of okay. Yeah.
You said that it's the adjoint action is diagonalizable, like lowercase ad or uppercase ad?
Sorry?
Like little ad or capital?
No, I look at I say that if G is a Lie group, then you have this adjoint representation from G to GL of the Lie algebra.
So it's
so you just act by, if you want, by conjugation. So this gives you a matrix representation. If we are mostly
by
interested,
lowercase, I mean the A.
yeah, for the you mean the derivative, yeah. The differential. You mean this?
Yeah.
This is a representation of the. This is not defined on G, but on the tangent.
Right. So it's not if you're saying it's diagonalizable, it's not like a vector space, right?
No, but now.
No.
Okay. Okay. Another interesting statement, I think, is the following. So let's erase Poincare recurrence. Actually, let me also give it as an exercise for the older students among you who already know what is an IRS and what is Borel density. It's an exercise that I never thought about it, but so I don't know how to do it. But it will be nice to do it. Prove Borel density. Density is C or S? Borel density for IRSs. You will all know soon what is an IRS, but now I still don't define it using Poincare. I don't know. I never thought about it, but maybe it's it. Okay. Another nice fact. So when you look at when we have G let G be the locally compact group, and gamma inside G lattice. And we want to know how gamma acts a subgroup of G. Usually it's a very interesting information, which we can deduce stuff from that. And in particular, a natural question is given H in G, a closed subgroup, one wish to know if gamma intersect H is a lattice in H. And sometimes the answer is yes, and sometimes no. I mean, typically no, if you just take a general, even you can see it in the plan. So we see this Z square is a lattice in R square. If you take a general alignment in an irrational slope, the intersection would be trivial. But if you take a line with rational slope, it will intersect it in a lattice.
Generally, a subgroup of a unimodular group is not one.
Yes,
So
also that. This is also, yeah. But it's even more than that. It's usually the intersection will not be a lattice. But here is an example that it is. So here is the case that it is. Let G be a locally compact group, and gamma G a uniform lattice. Let gamma in gamma and H be the centralized outcome. So that's all element in G which commute with gamma. Then gamma intersection of H is a uniform lattice in H. I can give two proofs of that. Yeah, maybe I'll start with one, and then maybe you tell me if you want to see another one. So how do you want to prove that? So in that case, you have a map H. You have a map from H to G mod gamma. Well, this is compact. I'm telling you of ideas of how to prove it. And it's map factor through H intersection with gamma. And this is compact. So if you know that the image is closed, then you will know that this is compact as well. And therefore it's a lattice. So that's one way to prove it. So one proof would be to show that the image of H in G mod gamma is closed. This would be one one idea of the proof. Another proof would be to take to start with a compact fundamental domain for gamma in G, and to construct from it a compact set which will contain the fundamental domain for gamma intersection H. So another, so this is one approach. Second approach, one can start with a fundamental domain for gamma in G and construct a compact fundamental domain for a gamma intersection H with A in H. And both approach works, and somehow they look very different. The reason to give both, if you want me to give both, the reason is that both approaches are very elementary, but if you slightly change the question, it becomes like some open problem, which is relatively famous. So maybe it works to give both. So let's start with one, and after you tell me if you want to see another. So proof. I will use approach one. Proof. We want to show that H times gamma is closed in G. This is equivalent to say, you say H times gamma. So if I denote this map by F, this is equals to F of H inside G mod gamma, and to say that a subset here is closed is the same as saying that its pre-image in G is closed, because that's how the topology on quotient is defined. So basically, this is the same as saying that the image of F here is closed. Right? So this is what I want to show. And okay, so let H and gamma n be a sequence in H gamma such that H and gamma n converge to something. And we want to show that this G, we need to show that G is inside H gamma. So how do we do that? So yeah, I have this gamma, this element gamma. So let's call this Gn. So consider the conjugation gamma by Gn. So it's gamma n H gamma n inverse H n inverse gamma H n gamma n. Now Hn is in the centralizer by definition of gamma. So this is just gamma n inverse gamma n, which belongs to gamma. Now, the assumption is that Gn converge to something. So Gn we know that we know that this converge to G inverse gamma G. So you have a convergence sequence inside a discrete set. This implies that eventually the sequence is constant. Right? Because it's converging and discrete. So what does it mean? It means that for large n and m, you have that gamma n inverse gamma n equals gamma m inverse gamma m, which implies that gamma m gamma n inverse belongs to the commute with gamma, which belongs to the center right there, which is what we call H. So you see, so for large n and m, so for n and m bigger than some constant, we have that. So we can write gamma n as something h n prime gamma n 0. Some, let's say gamma m. For some h m prime inside h. And so you see that Gn is Hn gamma n, which is Hn prime gamma n 0. And this converging to something, so it converges to something G, it converges to a limit G, which must belong to H times to this cosine. Okay. Let me know if it's clear enough.
What's that? So we can write gamma n0?
Yeah, for large, okay, maybe I should say it in a better way. I would say it like this: for large, for some n0 and all n bigger than n0, we have which means some. Now I'm doing that. I didn't. Okay. Yes, maybe that's more convenient. So this is one proof. Let me know if by doing that, I just say that this eventually this sequence Gn must be in a constant coset of H, and since H is closed, then the limit is also in that coset.
So you didn't use the fact that gamma is uniform to show that H gamma is clean.
I didn't use the fact that gamma is uniform. You're right. Right. It's a good consequence. Yeah, I didn't. Yeah, it's a corollary of this statement that whenever gamma is a discrete group, I only use the fact that gamma is discrete. So whenever gamma is a discrete group and H is a centralizer of an element, so in fact it shows more than we wanted. And yeah, so this is one proof. You want to see the other proof? Yeah, why not? And then I'll state the related open problem that then I'll state the problem that seems very close. Proof 1. Now proof 2. Which is by constructing a fundamental domain. So let omega in G be compact such that omega times gamma cover G. And I want to construct, we wish to construct maybe omega prime bigger than compact, such that omega prime times gamma intersection with H contains H. You see, then if you intersect this omega prime with H, you get a compact set which contains a fundamental domain. So I can tell you what is this omega prime. We will soon tell it explicitly. Let's see. So, given G in G, given G, given H in H, there is gamma in gamma such that H times gamma belongs to omega. But this gamma is not in H. That's my problem. So, but yeah, let's call it omega. Now, I consider this. I'm using gamma was the element that I'm centralizing. let's call this element gamma 0. Okay, so there is delta. Gamma is the element that defines H, right? So there is delta.
Gamma H.
Yeah, so we just keep the notation. So H is the centralizer of gamma. So now consider H delta gamma H delta inverse. So this, on one hand, H commute with gamma, so this is delta gamma, delta inverse gamma delta, so it's belongs to gamma. On the other hand, you can write it as omega inverse gamma omega. So it's belong to the compact set, which belong to the compact set omega inverse gamma omega, which is compact. So let delta 1 up to delta k inside gamma be such that delta I inverse gamma delta I exhaust. How do you write exhaust?
EXHAU ST.
Exhausts the finite set omega inverse gamma omega intersection gamma. And my claim is that the omega prime, which is the union of okay, if I should multiply from the right, from the left, or now I'm really confused. It will be let's gamble and write delta I equals 1 k omega is the required set. So I constructed some compact set that I claim that can be served as a fundamental domain.
You don't need to intersect it with H. So maybe
You
it's-
can. I said that it's contained.
Oh.
That's enough. Once you intersection with H, you get a compact set inside H, but it's still not a fundamental domain. It contains a fundamental domain. But from this, you can construct a compact fundamental. So I'm not sure if the delta I are from the left, from the right, and should come with inverse or without. But if you want, I can spend 5 more minutes and find out, or I can leave it as it is. Or I can look at my notes because this is actually the proof that I wrote in the notes. So that's
Give me the delta zone.
yeah. Let's do it. Okay.
So didn't you mean delta zone omega?
Give me a second. So
Omega.
first, yeah, okay. Yeah, so I think it should be like that. No, I think not.
אז דלתה זה עם גמא או עם אומגה? דלתה 1,
Sorry?
דלתה K.
What?
You said that delta 1, delta K in gamma, start with delta I, gamma, delta I, you have to exhaust. Shouldn't it be in omega?
Delta?
I mean, it's a subset omega inverse gamma omega. Don't you want to take elements in omega?
Let's see that this is a proof. Okay, now if it's written correctly, then it should work. So let's come back to the original element. And now I want to move it by an element in delta, consider again the same element, H, like before. We know that H times delta is in omega. Now, we know that there is I such that delta inverse gamma delta equals delta I inverse gamma delta. That's how we pick this finite set. Which means that delta I delta inverse belong to H, to the satellite of gamma. So I can write, so H times delta equals H times this element, delta I delta inverse, what? No. Right here, delta, want to write delta inverse times delta I is in H, and and I want to make some changes at the beginning and to assume that. Still okay. And this H times H times delta I H times okay. I want to H times delta inverse. I want to write it as H times delta inverse for H times delta. You can finish it yourself. No way. Why? Because if I try to follow, should I let you finish it? And the solution is just you see it's a few lines. It's just written. It's instead of letting me confuse me for the border. But it's basically this. This will be the required set. Okay.
So, again, what did you use the fact that omega is, I mean, if omega is not compact with finite volumes, then omega prime will still be finite volume, but maybe it's intersection.
No.
Is H
No.
must be this
If omega is compact, then this set is compact. If
Ah,
omega is just finite volume, this set could be the full group. Yeah. When you multiply two sets of finite volume, you don't necessarily get a set of finite volume.
So it's intersection with
But
gamma.
when you multiply two sets which are compact, you get a compact set. So this here we really use compactness, and here we really use compactness and yeah. So let me give some consequence of this. So example, let gamma inside SLN be a uniform lattice. Then it follows that gamma contains, let's say, gamma 1 up to gamma n minus 1, which are semi-simple and generate a commutative group. The group isomorphic to z to the n minus 1. How do you see that? You take the same so proof. By the exercise that I gave you before, by the exercise, gamma contains a regular semi-simple element. So basically an element gamma, which is conjugated to a matrix of the form alpha 1 alpha n such that alpha I, they are different. Which is smallest possible centralizer. So gamma contains such an element, which is diagonalizable and has different eigenvalues. So H, which is the centralizer of this element, is isomorphic to the diagonal group. And gamma intersect this with diagonal group is and gamma intersect this subgroup by a lattice. So this is an interesting phenomenon because if you want the translation of it, the geometric translation of it will say the following. So
this is true for any, because you didn't use the fact that it's a uniform lattice in the proof.
I use the fact. No,
The first proof.
The first proof didn't.
H times gamma is not.
The
is
first
close,
proof,
but
I just, the conclusion of the first proof was that the image of H in G mod gamma is closed. But if G mod gamma is not compact, the fact that it's closed doesn't mean that it has finite volume. But here, it's, and actually I will give an exercise, so related to that also. But the consequence here, for those of you who took my course about symmetric space, then you know that, let me just say it without writing, but it's good to write it in the notes. So the symmetric space of SLN R is a very interesting Riemannian manifold. For instance, the symmetric space of SL3R is the 5-dimensional manifold, which contains many flat planes. And if you have a locally symmetric space corresponding to SL3R, so it's a 5-dimensional manifold with non-positive curvature, and if it's compact, then it will contain many totally geodesic tori. If you apply this to a uniform lattice in SL3R, you will get a compact manifold which is locally isometric to the symmetric space of SL3R. And inside this compact manifold, you will find totally geodesic tori. This group, this H modulo, the intersection of H modulo gamma intersection with H will project to a tori in the locally symmetric space. And this is and now let me state this is related to, if you try to generalize it to, let's say, Hadamard spaces, then this is what is called the flat closing problem, which is a famous open problem, which says that if you have a Hadamard space and you have gamma that acts on it co-compactly, discrete, so you have a manifold of non-positive curvature, which is compact, and if the original Hadamard space has a higher rank, so it means it contains, let's say, a Euclidean plane or Euclidean subspace, which is totally geodesic and has a dimension k, then in the quotient you will find a k tors. So that's the flat closing problem, and it's an open problem in differential geometry, and nobody knows to approach it. While if you do the same problem for locally symmetric spaces, I gave you 2 elementary proofs. Okay, I got confused, but also the second proof is relatively short. You can see my notes. But and the difference between the general situation for the Hadamard spaces and locally symmetric spaces in that, for this problem, is that the group of isometries acts transitively. Lie groups act transitively on the symmetric space. For general Hadamard spaces, you don't have a rich group of isometries, and that makes the problem harder. You don't have group theory tools to deal with. So that's if you solve this problem for general Hadamard space, you will do some, would be important with that. And concerning your question concerning Ido remark, I will give an exercise. Let G be SL3R and gamma be SL3Z. Find gamma in gamma semi-simple, just diagonalizable element in SL3Z, such that the centralizer of gamma intersect gamma is cyclic. particular, it is not a lattice in a CG. Because CG of gamma has larger dimension. The centralizer of an element in SL3R is at least 2 dimensional. The elements with smallest centralizer are regular elements. For them, the centralizer is isomorphic to the diagonal.
When you say is CG, you mean isomorphic to Z?
Yeah, isomorphic to that. Yeah. The centralizer, if you intersect it with gamma, it's a straightforward it's a straightforward exercise. You find such a matrix which small intersection, and then you have this. By the way, you can get so in particular, the analog result is not true. There is a theorem of Garland and Raghunathan, which says that actually, also in that case of non-uniform lattices, you can always find a tori of the right dimension in the quotient. That's in fact, but that's a term that I will not discuss here. So remark. Weizmann, Raghunathan. Proved that even in that case, in that generality, the quotient, the locally symmetric space will contain a tori
So you have gamma 1 to
of the
gamma
right dimension of the rank dimension. Flat, totally geodesic tori of the rank dimension, but it's not coming from arbitrarily semi-simple regular element like we did in the comp. Yes. What?
So the fact that we can find gamma 1 to gamma n minus 1, which generates a to n minus 1 is not generated, it's equivalent to that.
Sorry? Yeah.
Okay.
Yeah. So you can do the same is true here. Yeah. Actually, this is true for any lattice in SL and R, but it's much easier for co-compact lattices, and it's a theorem of Garland and Raghunathan in that case. Do I want to say anything more about this? Or yeah, let me say another remark without writing. Also, applying this idea about centralizer, you can get a lot of other interesting consequences. For instance, in SL3R, you can find lattices, uniform lattices, which contains singular elements. I'm talking without because, it just to tell you why this lemma is important for application, because it tells you a lot about the geometry. And for instance, in SL3R, in SL3R, there is a uniform lattice gamma containing an element of the form containing a singular element, singular semi-simple element. So it's an element gamma, which is of the form lambda, lambda, lambda minus 2. So you see it has two eigenvalues that coincide. The centralizer of such an element is bigger. The centralizer, C, G of gamma, is actually isomorphic to GL2. It's a three-dimensional, four-dimensional group. If you want, isomorphic to the group, isomorphic to GL2. And if you apply the same reasoning for the centralizer of that element, you will see that still the intersection of this GL2 R with this gamma will be a lattice in this GL2. Now again, for those of you who know a bit about symmetric spaces, the symmetric space of GL2 is not an irreducible one, the symmetric space would be R times H2. The symmetric space of SL2 is H2, and GL2, you can think of GL2.
Why would it be a lattice if gamma is not frequent?
No, there is a uniform, a covalent lattice, yeah. So you have such a uniform lattice, and then you will get something like that. In the quotient manifold, in the five-dimensional quotient manifold, you will see in the quotient manifold something of the form a surface was a circle, which comes from the quotient of this R times H by this co-compact group will be something like that. So you see that from this naive lemma, I gave you two proofs of this lemma, and I tell you that there are plenty of applications, geometric application, dynamical application, and it's also related to a famous open problem that is wide open. Okay, so let's have a.
This is a quotient, though.
Yeah, this you can see something like that inside. So this will be the circle. You will see this as this. This will be the quotient of H2 times R modulo the intersection of gamma with this GL2. And this will be inside G mod K mod gamma, which is the five-dimensional manifold corresponding to this. Okay, this is some remarks for those of you who knows a bit of symmetric spaces, but in general, this is it's an interesting lemma that centralizer. And actually, let me give you another exercise, which will be easy for you if you understood one of the proofs that I gave you for the lemma. Here is an exercise. Let G be a locally compact group and gamma a uniform lattice. Let delta inside gamma be a finitely generated subgroup. Then the centralizer of G of delta intersect gamma is a uniform lattice in the centralizer. So the idea is to exactly what I did with one element, do it finitely many elements, which are the generator of delta. Now, it's interesting because it tells you that if you start, it's not very hard. There is to show that if you have a uniform lattice in a locally compact group, and suppose the locally compact group is the Lie group, or at least that it is compactly generated, not a too big group, and a uniform lattice is always finitely generated. A subgroup of a uniform lattice, if it's finitely generated, I wanted to say that it's because it's a lattice in some smaller group, but this is not true because delta may have much larger center. But anyhow, this is still this exercise, and it just follow what either proof 1 or proof 2, but instead of considering one element, consider several. And yeah, okay. So let's have like 10 minutes break and continue. So let me just remind that I gave you one open problem which is supposed to be hard, the flex loading problem. But after the break, I will discuss the theorem of Mosto about co-compactness of lattices in solid group, and then I will give some open problem which I think it's very good problem for students. So it's doable and interesting. So I think it's doable. And okay, so let's have 10 minutes until 22.
It's open.
It's recorded anyhow. So basically, I want to prove the following lemma or proposition. So I'm discussing the following issue. So there are many examples of non-uniform lattices, non-uniform, non-compact manifold of finite volume. Usually we imagine them as something which has a cast that becomes like narrow and narrow when you go to infinity. There could be much more complicated. So this cusp, the geometry of this cusp could be quite hard to understand. But in some cases, you don't have non-compact lattices. So it's a definition. Group, a locally compact group has property M if every closed subgroup of finite co-volume, every cofinite subgroup is co-compact. So this is called property M, and M is after Mosto, but it could be also after Malcher, because Malcher proved before that nilpotent group is property M. I want to show that solvable Lie group is property M. So,
That's a really stupid question. Cofinite means like a quotient is finite at the very
Yeah.
end, not finite.
right, cofinite means that G mod H, H is cofinite, means that G mod H has a finite G invariant measure. So if H is discrete and co-compact, then it's easy to see that it's cofinite. In general, if H is co-compact, it doesn't mean that it's cofinite. We have example like the projective line, which is a compact quotient of SL2R, but it doesn't carry an invariant measure. So here is a remark that actually when most of
this equivalent to finite measure.
yes, if H is discrete.
And if no, and if H is not discrete.
If H is not discrete, we usually don't discuss fundamental domain because the how measure, the measure of G mod H is in a sense singular to the measure on the how measure. So, okay, mathematics develops, and when most of wrote about this property for solvable groups, he was not aware that he also proved the converse. Most of prove, I'll get to it soon, that for solvable group, if you are co-compact, then you are cofinite, and vice versa. But one direction is easy today due to amenability. So remark, proposition. If G is amenable, or for amenable group, cofinite implies compact implies cofinite. For amenable groups, and this was somehow, so if you look at most of paper about solvable group, it's an analog paper which is quite complicated, and he worked he did non-trivial work there to prove that for solvable group, if a subgroup is co-compact, then G mod H is a cofinite measure. But if you apply this notion of amenability, which people today apply all the time, but even 40 years ago, people wouldn't do that. And you see many good papers in the annals that prove something which is trivial if you think about this notion of amenability. Like not most of the theory, because most of it also is another direction, but some even paper of Silverstone and so let me just finish that. So this is indeed proof. So if you, I think you all know from my course last semester what is amenable means. Proof G mod H is compact. G is a compact G space. Hence carries an invariant probability measure. That's it. But for H, when H was discrete, then you don't need amenability. If H is discrete and co-compact, then it's the lattice. That's general indeed. So this is just a remark that I want to say before going into stuff. You had a question?
But even for minimal groups, not every subgroup meets an invariant measure.
No. If for amenable group, if it's not co-compact, no. So these are general stuff. Some more general stuff that I will want. Here is a nice lemma. Let G be a local group, and then H, G, cofinite. Let F containing H, containing G, be a closed sub. Okay, I will do it and then so let H be a closed subgroup. Then F is cofinite. And in fact, let's do it differently. Let's do as follows. Let's more general. So let G be a locally compact group, and H inside F inside G closed. Then the following are equivalent. The following are equivalent. One, H is cofinite. Two, it's cofinite in G. Two, H is cofinite in F, and F is cofinite. So in particular, I will use only the easier part, that if H is cofinite in G, then F is also cofinite in G. Moreover, if F normalizes H, then F mod H is common. Okay, that's.
I mean, F normal H just means that H is normal in F, right?
Sorry. Yeah, if F is containing normalizer of H, then H is common. Actually, it's good that you came. I want to suggest a problem for you and Tal, maybe a better problem than the one you're thinking now.
Moreover, all the assumptions it requires are the first sentence.
Moreover, it's just additional. So maybe that's a remark. That's a different lemma. I will keep it for the next lemma. If you want,
you said that whenever normal sum was defined.
That's a remark. A remark that actually I should say after the book. But if H is normal in G and cofinite, then H is uniform. That's because G mod H admits a finite measure. So G mod H is a group with finite measure is compact. So okay, so let me move the lemma. Actually, I will use only the easy part. So proof. So if H is cofinite, then the map, then the map from G mod H to G mod F, the push forward, if I call this map pi or P, let's call this map psi, then profile with measure M. Then if the push forward of M is a finite measure, G valid measure on G mod F. So you see immediately that F is cofinite. Now, if F is cofinite, then this implies that the delta of G restricted to F is delta of F because F is cofinite, which implies that delta of F restricted to H is delta of G restricted to H, which is delta of H. We'll delta of the modular tau. So this implies that F mod H has an F invariant measure. And I claim that it also must be finite. Let's denote this by okay. This measure, let's call it mu, and here we have a measure we call nu.
Why did we not finish now?
Sorry?
What's about why did we not finish now? It's not finite measure?
I want to show that it's finite measure. I want to show that mu is finite. I claim that from mu and nu I can define mu and nu together gives me a measure on G mod H, and you see now we can define a measure on G mod H using mu and nu as follows. So let F from G mod H to R be a function. So the integral of F with G mod H, I define it to be the integral, the first integral F G first integral over F mod H yes d mu, and then I integral this d nu, and that's defined that defines a measure on G mod H.
Didn't we start with the measure on G mod H?
Yeah, I have some measure on G mod H, M, and now I define a new measure on G mod H. By uniqueness, the measure on homogeneous spaces is unique up to scale. By uniqueness, this measure is finite. It's actually proportional to M. It's a scalar multiple of M, so it's finite. But you see that it could be finite only if this is finite, which implies that mu is finite. Or maybe I should say before uniqueness, this measure is finite. Okay. It's easy to see that mu is finite, if and only if this measure, let's give it a name, the
Sigma.
sigma. See this sigma. Okay. Okay. Mu, if and only if sigma is finite, but sigma is proportional to m is finite. Okay. So this finished the proof. So it implies that that mu must be finite if m is finite, but it also shows the other direction. It shows that also if it also shows the other direction, because if we have finite measure like this and finite measure like this, then we can prove finite measure here. So it also shows that 2 implies. So I showed you that 1 implies 2, but this line also showed that 2 implies.
On the right-hand side, it's a measure on F mod H, so G needs to be in F.
This is a measure on F mod H. So what I mean here, so I do here, do know F, well so here I think not F F is the function. So let's go the function, let's go phi, and then F will be, I can think of element here, and then after I integrate here, after I integrate, I will get, this will be something on GF. This will be the value. So after this will be, this is a function on G mod F. So you only care what is the coset modulo F after you integrate in F. And this you can integrate with respect to. That's
maybe you need to before the F mod H to take a different coset.
This is the, here they develop. Sorry? So
In the right integral, you every time you integrate on a different coset. You choose the concept.
No, but the G is inside the signify.
That's helpful. And now I integrate here GF. So this is a proof that 1 implies 2, but also this line also shows the converse, because this 2 finite measure define the finite measure of G mod H. But this is a nice lemma, but I'm going to use only the very easy part of it, that if G mod H is a finite measure, then you push it and you get the finite measure of G mod H. So I see that you will have to come next week as well, because I will not have time to present the problem that I want, but let's now discuss nilpotent group. So I want to prove the following proposition. Nilpotent group have property M. Furthermore, nilpotent groups are amenable, so furthermore, if N is nilpotent, locally compact group, and H in N is closed subgroup, then H is cofinite, meaning that n mod h is finite h is Rx measure if and only if h is uniform. N mod h is compact. And the proof, so this direction is because nilpotent are amenable. And we know that for amenable group, uniform imply finite. For the other direction, I will argue by dimension. Or by not dimension, because there is no dimension. It's a general locally compact group, it's not a Lie group. So I will argue by the nilpotency rank. So that's a general thing you need to know when you talk about the nilpotent group. Anything you can prove, you usually prove by induction. The induction could be either on the dimension or on the nilpotency rank, or sometimes on other stuff. Hirsch rank, several. So what is the proof? So by induction on the nilpotency rank, the base case is that n is a billion. Now we know for a billion group, we already know that cofinite it implies co-compact, because if you have a cofinite subgroup, the quotient, as in the exercise before, the quotient is every subgroup is normal. If you have a cofinite normal subgroup, then it's the quotient is finite Haar measure, so it's the base case is that n is a billion, for which we know that. Okay, if you want, if n mod h is finite measure, it's the Haar measure n mod h. So the base case is easy. So now we do we argue by induction on the nilpotency rank. So nilpotent group have center let Z be the center of N. And consider let F be Z times H plural. So F is cofinite in N because it contains H, so by the previous lemma. But but what is F? I mean, now I can quotient by this. So N mod F I can identify with N mod Z mod F mod Z. Both of them contain this Z, which by induction and since the nilpotency rank rank of N mod Z is the rank of N minus 1, then by induction is compact.
What do you mean by rank?
Sorry?
What do you mean by rank of the?
Rank, the nilpotency rank. So the nilpotency rank is the length of the central
Series.
series. The upper or the lower, they have the same length. So I look. So what does it mean that C is you have the center of N, which is contained in the preimage of the center. Okay,
Yeah.
you know what that.
Mhm.
So the nilpotency rank are N. Okay, so now we are left to show that F mod H is compact. But H is normal in F mod H. In F, or H is normal in more well. More well. H is normal in F because H normalizes itself and Z converges with everything, so Z normalizes H. So Z times H normalizes H, but normalizer is always closed. Normalizer of a closed subgroup is always closed. So H is normal in F, and therefore, and we know by the lemma before, more and H is cofinite in H. So F with H.
H cofinite in G, right?
Sorry?
H cofinite in G.
H is cofinite in G. So yeah.
Yeah.
So it is implied by the lemma we had it's also cofinite in F. Okay, that's finished. So you see, it's basically elementary statement, and actually, I think I have time.
Why did you need the more over part? What? It's taken to use.
I wanted to show that H. I wanted to show that H is co-compact in G. So now I know that it's co-compact in F, and F is co-compact in G. So it implies that H is co-compact in G. Not G, N. Okay, what about solving? That's the next step. So this would be the next. So I don't. 50 minutes is not enough. But I want to tell you. I want to tell you the following. So there is a theorem of Mostov. The solvable liquid have property M. So in solvable Lie group, every lattice is co-compact, or every cofinite subgroup is co-compact. That's the theorem. And most of also prove the other direction. So every cofinite, co-compact subgroup is cofinite, but that's now trivial biomutability. And so I want to prove this theorem. But you see, now we'll fix ourselves to Lie group. And for nilpotent, we didn't do anything. It was just an easy statement. So my question is, what if you remove this Lie group?
But we stay connected because before we didn't have connectedness. Sorry? Not only legal, but also connectedness.
Yeah, connected is not so important.
So to come back to something we are.
Let's say I think solvable Lie group would be enough. I said connected because it's simplified the proof, but solvable Lie group.
Not even finitely many connected people.
I think you don't need finitely many connected components. For this statement. But the question is what happens for non-connected. So actually there was a conjecture of Benoit and Kant that the same holds for general locally compact group, and it turned out to be false. So remark. So example. Is a counter example to a conjecture of Yves Benoit and Jean-François Kant. So it will be some totally disconnected group. So let's P and B primes, which go fast enough. The condition. And I want them to go fast enough, such that the product of Pn minus 1 is finite. And now let G be the following group. Right?
If the product is finite and it goes slower or faster, I don't know. We see this need faster.
It's an infinitely many primes. So it's an infinitely many primes.
Pn max 1 is smaller.
So this is a number which is a number that is a bit larger than 1. If P is very large,
So you take large.
Yes. Large the goal part. And basically, okay. So let G be the following group. So I take some compact group. And I look at the field of Pn elements, and I look at the multiplicative group, and I multiply all of them, and semi-direct with the direct sum of this is a discrete group. Now let's consider let gamma be the group of all elements of the form all sequence AN an minus 1, such that an is in Fpn, and an equals 0, except finite for almost all n. Oh. This is a bit strange example, maybe, especially. And then I claim, one theorem, gamma is a non-uniform lattice.
Can you explain what gamma is again?
Gamma, yes, you see, so this is a product and this is a sum, but each factor here acts on the only on the corresponding factor. And so in the end factor, I take an element in Fpn star, sorry, an equals 1. So I take an element in the multiplicative group, and I take here the element minus 1. Then I claim, in particular, I claim that this is a group.
So the minus 1 is over all the an.
Sorry?
It's not the index n minus 1, it's an minus 1.
Yeah. Yeah, that's better. Okay, I will explain next time. I want to, actually, I will explain this example next time. The point is that this is a counterexample to, this is an example by Uri, Kapras, myself, and Shahar Moses. And the point is that we find a locally compact group, which is actually abelian. It's abelian of it's solvable of step 2. The commutator is abelian, and it has a non-uniform lattice. So that's a counterexample to the conjecture that was supposed to generalize. Actually, the conjecture was that amenable groups are property n. This is a very much solvable group, which is not amenable, and which is not a property n. However, this group is not compactly generated. So let's write here compactly generated solvable group. Oh, I mean, Lie groups, if it's not compactly generated, then it means that you have some discrete portion which is not finally generated. And,
so this is not necessarily true for infinitely discrete, not finite.
Compactly generated. I think you don't need just in a
I think it is true for infinitely discrete, non-finite generated.
If you have infinite for discrete group, of course, for finite and for compact is the same.
Right.
So for discrete group, so I don't care. I don't really need the compact. But here is the question. This is the question that I'm reading for you. What if G is compactly generated? I think it's a very interesting question. If you like this part of mathematics, it's an open question and interesting and I think a very natural result. Is it true that solvable compactly generated groups are property n?
Is G not even locally compact?
No, G is locally compact. I will discuss this next time. I'll explain it. G is locally compact. I also going to give you a very elementary proof for most of the theorem, like almost as short as the important group. So although it was at the time it was like an honors paper, which is quite complicated, and then Raghunathan wrote it much better proof in his book about most of theorem, much shorter and more elegant than most of proof. But I will give you even much shorter proof for that. But then you will see that it relies on some Lee theory, and it's not true in the generality of float and compact group. But then there is this question which I think should be solved. So I suggest we this. Okay, I'll discuss this stuff more next time. So it will postpone by another week the promised Margulis proof for Borel term that I aim for. Okay, we'll do it after the video chapter. Okay, so any more questions?
Give an example of a group of all lattices have property n, like all you have only uniform lattices, but the group is not property n.
That you have cofinite subgroup.
If I'm a lattice, I must have the uniform, but this subgroup doesn't have.
Usually, in fact, I don't even have a good example of a non-discrete subgroup which is cofinite but not compact. Usually, yeah.
Just compact times the group.
Yeah, but that's okay. But that's not a good example. No, I don't have a good example. I need to think if I have a good example of something which is a non-discrete subgroup which is cofinite but not compact. Usually the non-uniform finite volume stuff comes from the discrete groups. Don't know if they can count. Yeah, but yeah. You know, I just want to say it's more interesting, of course, for discrete group, but all you can prove in the more general setup of closed circuits. That's why.
You think the answer is yes?
I think the answer is yes. I expect it to be yes, but even if you construct counterexamples, I know how to prove it for metabillion groups. So if you have such counterexample will not work. I know how to prove it for nilpotent by nilpotent, semi-direct product of nilpotent group and nilpotent group. But then I don't know further. Yeah, I don't know about trees there. So, but it's a good question. It seems to me that it should be solvable and should be doable and not too easy, but doable. Okay, so let's. So I gave you one really hard question. I don't know if it's hard in mathematics. Sometimes we think that problems are hard, but we never really know until the end. Right? If someone solves it, sometimes it turns out to be easy. So flat closing problem that I mentioned is assumed to be hard. So I wouldn't give it to a PhD student as a project. But this thing, I don't think should be too. This could be a good project, or if you like this type of thing. Okay.